Hi there, welcome back to this channel. Following the video that we made yesterday on electrostatics, today we are going to be discussing the Coulomb's law. We're going to be using these three problems to solve, we're going to attempting these three problems in order to understand how to solve questions on Coulomb's law, questions involving Coulomb's law. But basically, we are going to start with the vectorial form that I did explain yesterday, but I'm going to emphasize it a little bit more, and then the principle of superposition as it applies to Coulomb's law. All right. Now, the vectorial form. Now, the vector form simply refers to the vector notations used when it comes to analyzing Coulomb's law in a 3D perspective. So we already know that the force of attraction, according to this guy, Coulomb, states that the force of attraction is directly proportional, already introducing the constant, directly proportional to the product of the charges, and inversely proportional to the square of distance r between them. Now notice that there is no arrow on these two charges because of their being a scalar, they are being scalar quantities. So this guy is a scalar, this guy is a scalar. Charges are scalar. I did explain this. It's one of the fundamental property of charges. While this guy is the displacement, we call this guy position vector. Now displacement, it might confuse some students because they feel in electrostatics we are talking about charges at rest. Yes, of course, but there might be, when there's force of attraction, there might be relative motion. Is that clear? Motion that it is not equal to current electricity. Exactly. Current electricity, charges are flowing speedily. Do you understand? But there is relative motion when there is attraction or repulsion. Is that clear? Okay, so that's why there is displacement in this case. So this is position vector. We represent it by R with an arrow. Is that clear? Then this one is the unit vector. So this one is the unit vector, R hat or caret, R hat. That's what we pronounce it though. So the point is this, that this unit vector only shows direction and its magnitude is 1. It has a magnitude of 1. So 1 multiplied by this thing is still the same. It doesn't change it, but it represents the direction. So we could have the three different directions we could have in the Cartesian geometry. If we make it a 3D plane, we're going to have in this direction, y direction, we'll call it a j vectorially. Then in this direction we have I, and in this direction we have k. Okay, the y-axis j, the x-axis I, so this will be positive I, positive j, negative I, negative j. Z-axis k, positive k, negative k. Okay, so that's just to explain what that is. Now, of course, we now use notations based on the force affecting a particular referenced charge. Okay, so for example, if you want to deal with, if there are 2-point charges now, let's say this was positive and this was negative. Okay, now if these were positive, I want to this, let's call this Q1, let's call this Q2. I want to analyze the force on it. Now the force on this guy is going to be termed the force on 1 due to charge 2. And this one, the force on this guy, is going to be the force on charge 2 due to charge 1. Is that okay? F12 means force on charge 2 due to charge, force on charge 1 due to charge 2. Here, force on charge 2 due to charge 1. I hope that is clear. Another thing to clear is this. The position vector of this guy is going to be represented this way. The position vector of 1, 2 will be 2, 1, because it's going to be, because we will be describing the force on 1 due to 2. So it means that we are at 2, the force is from 2 to 1. Does that make sense to you? That's why the position vector is written as 2, 1. I hope that is clear. Then the force on charge 2 due to 1 is going to be written this way, but the position vector is going to point from 1 to 2. Pointing from 1 to 2 means that the force is due to 1, right? So the position of the force is from 1 on 2. Does that make sense? So that's R12. Okay? But the vector, the unit vector is going to be written as this: r hat 1, 2. Now 1, 2, because unit vector points from the direction of the charge itself. Is that okay? So this will be unit vector from 1 to unit vector from 1 to 2, pointing from 1 to 2. Then this will be the unit vector pointing from 1 to 2. This will be from 2 to 1. Does that make sense? So don't misplace them. This is unit vector and this is position vector. Okay, they do have a formula. So if I were to find the magnitude of R21, for example, depending on the convention that your textbook uses, the formula is usually for the convention that I use. For example, R position vector 21, R21 will be equal to R2 minus position R2 minus position R1. Does this make sense? Then for R12 will be R1 minus position R2. Then your unit vector R21 will be equal to the magnitude here, this value R21 minus R2 minus R1 all over the magnitude of R2 minus R1. And of course, it's the absolute value. So either way you put this one, you're going to get the same answer. Whether you put R1 minus R2 or R2 minus R1 here, because it's the absolute value you are taking. So this is the value of the unit vector. This is how we calculate for unit vector. But if you want to calculate the absolute value here, R1, if I say, for example, the value of charge of position vector R21 is going to just be the square of the values that are given. Is that okay? You are going to square the values that are given. So let's say, for example, you are given something like 2i plus 3j or minus 3j, for example. The answer is going to be the square root of the square of this plus the square of this guy with its minus sign, minus 3 all squared. And this gives us the square root of 2, 4 plus 9, right? Minus 3 is 9, so 4 plus 3, 4 plus 9 rather, that is 13. So our answer is going to be the square root of 13. So you see it's going to be a whole number here. So that will be what you have here. While this guy is still going to have the direction I or J in it. Does that make sense? Okay, so that is all this thing that we use, the notations we use, I just analyzed here so that when I begin to solve questions, you're going to understand what I'm doing. Okay? So that's pretty much it. Now, so it means that we can rewrite this equation F from F force on 2 due to 1 will become K Q1 Q2 dot position vector R21, because it's the position of that charge over position of charge 2, right? Over the vector from R2 minus R1 all squared. Now listen, here, I could position vector R2 minus R1. I could write this as R1 minus R2. It's going to give me the same answer. Is that clear? But if I wanted to write the notation in simple form like this, I'm going to have R12. Is that clear? So that if you see that, you won't say the person made a mistake or it doesn't, it's not clear to you. I already explained that here. You do well to rewind the video to understand what I said. Okay, so let's go on to solving the questions then. So, and of course, we can introduce, depending on what the question says, we can introduce the formula that I talked about, where if we had, we're given relative permittivity and all those things, and permittivity of medium, but I don't think there's anyone that has to do with that here. So let's solve the first question. It says, two charges, Q1, so Q1 is 500 microcoulomb, and Q2 is 100 microcoulomb are located on the XY plane. They are located on the XY plane. So let's draw our XY plane. At position R1 equals this, 3jm. So it means that our first charge, Q1, is at 3j here, right? 3 meters here. Let's put it here, 3 meters. Does that make sense? 3 meters. So, and our R2 is on position 4. Now, J, because I know that it is here because J is y-axis. I already said that, right? Then R1 will be 4, that is I, because and that's going to be x-axis. So 4, if this 3 should be longer, maybe around here. So that will be 4 meters, okay? I hope this is clear. So our charges are going to be connected by this line. You understand? Because the force of attraction or repulsion, then will it be attraction or repulsion? They are positive charges. So it's going to be what? Repulsion. So it's going to act along this line. Because vectorially, if we state the coulombs, I will say that the force of attraction or repulsion between so and so is proportional to the two charges, product of two charges, and inverse proportional to the square of the distance between them, and acts along the line joining or separating the two charges. Does that make sense? So the force that acts in this direction now, if this was Q1, right, and this is Q2, the force here is going to be F, the force on charge 2 due to 1 is going to act in this direction, and F, force on charge 1 due to charge 2 is going to act in that direction. Does that make sense? This one will act in this direction, this one will act in that direction. But our arrow at the top is always facing here. Is that okay? All right. Okay. So that's that. So it means that our position vector here is going to be R1, 2, and it's going to face this. Our position vector is going to face this direction here, and our position vector here will face this direction. That is R2, 1. Okay. Anyways, let's go on to solving it. Now, find the force exerted on charge Q2. So we are looking for the force on this guy. So what we are looking for is basically F21. F2, 1. Okay, so the first thing to find is let's write the formula. So our formula will be K. We're not giving K. So for all our questions, let's use K equal to 9 times 10. Let's take K equal to 9 times 10 to the power 9 Newton meter squared per coulomb squared, I think. Okay, so KQ1, Q2 over, now in this case, because we are pointing from 2 to 1 and our positions are given, it's going to be R2, position vector R2 minus R1 all squared dot unit vector R21. Okay? R hat 21. I hope that is clear. So in this case, so let's find this value first, which will be our position vector from 2 to 1. That becomes R2 minus R1. Okay? So let's find this value first. R21 will be R2 minus R1. And what is R2? What's position R2? That's 4, right? 4 in what direction? In this direction. In fact, you're already given 4i meters. So that becomes 4i minus R1, that's 3. 3j, right? 3j. Both are in meters, right? Okay, so this is going to be our R2 minus R1. All right, so in this case, in that case, let's find the magnitude. Let's find the magnitude. Remember I said we'll find the magnitude. The magnitude is just, we square this value, we take the square root of the square of this guy. Square of this guy is going to be 16. Okay, so let's say 4 squared plus minus 3 squared. Okay, so this becomes the square of this is 16 plus 9. That becomes the square root of 25, which is equal to 5. Okay, so that's the magnitude of this value here. So Then let's find our position vector then. Our position vector therefore becomes, our position vector R2, 1, R hat 2, 1 is going to be, the formula is this over the magnitude, right? So that becomes 4i minus 3j, okay? I hope that is clear. 4i minus 3j all over the magnitude. Remember the formula is R2 minus R1 over the magnitude of R2 minus R1. R2 minus R1. Okay, so in this case, this will be I, yeah? It already comes with the I and J, okay? So this is going to be 4i minus 3j from what we have there, all over the magnitude we got was 5, okay? So you can solve this by isolating, by separating the fractions. So we have 4i over 5 minus 3j over 5. This becomes 4i over 5. That becomes 4 over 5. That will be 0.8. Yeah, 40, that's 0.8. 0.8i and 3 over this, that's 6. 0.6 minus 0.6j. Okay? What else? What else? That's all. Okay. So this is the value of our position vector. So we can go on to solving this now. So recall that our F2, F2, 1, force on 2 due to 1 is equal to this guy, K times this. So let's just plug in all our values. So you know what I will do? I'm going to clean this part now. I'm going to clean this part. Okay, then I'll clean from here. So our F will now be F, force on 2 due to 1 will now be equal to K, which is 9 times 10 to the power 9 times Q1, which is 500 micro is times 10 to the power minus 6, right? Times 10 to the power minus 6. Okay, I'll link the video in the description where I talked about all the notations that we use, micro, nano, pico, zeta, etc. So times 10 to the power minus 6 times 100 times 10 to the power minus 6, okay? All over the magnitude, which is 5. In meters already, since it's given in meters, so we just go on with times 25. We square it, right? 5 squared. Then times our position vector, which is this, okay? So all of this multiplied by 0.8i minus 0.6j, okay? So F2, 1 will be equal to this times this times this. Let's machine the top. We have 45 times 1, 2, 3, 1, 2, 4. 45 times 10 to the power 9 times 10 to the power 4 times 10 to the power minus 12. Okay? All over 25. Then times 0.8i minus 0.6j. I hope this is clear. Then what we have is 10 to the power 13 minus 12. That's 10 to the power 1. So 9 divided by 5. That will give us 1.8. So we have F2, 1 equal to 9 over 5. That is 1 over 4 over 5, which is 1.8. 1.8 times 10 to the power 13 minus that, that's 1. Then times, so that's like 18. 1.8 times 10 is 18, right? Okay. So this becomes 18 into bracket 0.818i plus minus 0.6j. Okay, so F2 comma 1 will be equal to this times this. 18 times 8 will give us 4, 6, 1, 4. So that will be 14.4 I minus 6 times that. That will be 8, 108, 10.8J. Okay, so in vectorial form, this is going to be our answer. But we can still find magnitude if we wanted to. So, but since our question is like this, I guess we can just leave our answer this way. All of this in Newton. You must put the unit. So this guy in Newton. Let me confirm this. 18 times 0.6. 18 times 0.6. 108. And 18 times 0.8. 144. Okay, so 1.4. So this is it. So if you want to find your magnitude and direction, just take the magnitude, absolute value, the square thing that we talked about. Then if you want to find the direction, take tan theta equal to summation fx over summation fy over summation fx, and then you get your answer. Okay, so that's that for the first question. All right, let's solve the second question. For the second question, it says 3 charges Q1 is equal to 6 microcoulomb. Q2 is equal to minus 0.6, minus 6 microcoulomb. And Q3 is equal to 4 microcoulomb. Okay, so it already tells you that between this and this, attraction, between this and this, attraction, between this and this, repulsion. Okay, allocated at 0.6 I hat, minus 0.6 I hat, and this, respectively. So we are going to give them those values respectively. So for Q1 will be located at minus 0.6 I. So we'll start from origin. Let's say we pick this point as origin. So 0.6, maybe meters, the unit is not given there. 0.6, so negative in this direction, and I on x-axis, right? So that will be 0.6 here. This will be our origin. Then the other, so this is our charge, our first charge, 6 microcoulomb. Okay, so that's what we'll put here. But we know that this here is 0.6. I hat, or it just tells us the direction. Then Q2 is going to be in this direction. So this is Q1. Q2 will be in this direction, the same length, 0.6, but in the other direction. Do you understand now? So, yes. So this becomes, and the value of this one is negative 6 microcoulomb, opposite of this, minus 6 microcoulomb. This is Q2, and that's in this direction, 0.6. Okay, then the Q3 is now located at plus 0.8J. That's up, right? From origin, upward. That will go like this, right? Okay, so this will be Q3 and 0.8. Okay, and what's the magnitude? 4 microcoulomb. Okay. Now, we are told to find the net force on Q3. So the net force that will be acting on charge Q3, right? On charge Q3, this charge Q2, charge Q1, okay? So as it is, the force is going to act along this line. The force on 3, F3 F31 will act along this line. Then because it's the line joining them according to Coulomb's law. So the force on 3 due to 2, that will be F32, we act along this line. Because it's also, is it repulsion? Q3 and Q2. Q3 is positive, Q2 is negative, sorry. So it's going to act, not repulsion, it's going to act in this direction. So this direction you see here is going to be F force on 3 due to charge 2. Okay? So I hope this vector diagram is clear. If it's not clear, then you have to just rewind the video and try and understand it. This direction is F31 because it is the force on charge 3 due to charge 1 and it is repulsive. So it's going that direction. You're going to push it towards that direction. And of course, this one is even greater in magnitude. So it will be pushing that one away. Then this one, greater in magnitude, we attract this one here. So that's why it is in this direction. So we can as well go on to find the magnitude of this place or the magnitude of this place if you want to. Okay? But since it's saying we should find the net force on the charge 3. Okay. So this is where the superposition principle now comes in. Superposition principle. Now, it is not all the time that we are going to have all our forces arranged on a straight line. Is that okay? They can be arranged in a 3D geometry. And so how do we resolve them? How do we find the net force on them? And that's where this principle of superposition comes in. Because forces that are not in, forces that are more than one, that are more than two rather, and that are not, when forces are more than two, that is when we have a limitation of the Coulomb's law. So that's why we now use this superposition principle to solve or resolve that problem or overcome that limitation. So what it says is that when there are more than 3 charges, when there are more than 2 charges, that the net charge, the net force on any of the charges is going to be the vector sum of the individual forces, the vector sum of the force due to individual charges on that charge. So what that is saying basically is that if I have a charge Q0 at origin and I have different forces acting on it in different places, then the F net, the force on my charge Q0 due to the net force on charge Q0 will be equal to the sum of the vector sum of the charges of the vector sum of the F0, the force on charge Q0 due to force 1, charge 1, plus the vector sum plus the force on Q0 due to 2 plus force on Q0 due to 3, plus force on Q0 due to any number of charges. Does this make sense? Okay, so that's just it. I'm going to do the vector sum of the individual charges, of the force due to individual charges. Okay, so that's the superposition principle. And that's what we'll be applying here. So first, let's find F. So I'm looking for the net force on F3 net now will be equal to F31, plus F32. Okay, yeah, there are just two more charges, 2 other charges acting on Q3. So these are the things we are looking for. So let's find F31 first, that is force on charge 3 due to charge 1. So we have F31 equal to So the formula we'll be using will be what? Do we have, okay, we have vector notation too. So the formula is going to be K, Q1, Q3, Q1 times Q1 over the position vector we're going to be looking at is the position vector that points from 3 to 1, the value of that. Is that okay? Actually, our value will point from 1 to 3, but the absolute value will not change. So square dot the r hat 3, the unit vector that points from 3 to 1. I hope this is clear. Okay? So our F31 therefore, F3, 1 will be equal to K, which is 9 times 10 raised to the power 9 times Q3. Our Q3 is 4 times 10 raised to the power minus 6, multiplied by Q1, which is 6 times 10 raised to the power minus 6, all over, dot. Now we have to find our position vector and unit vector. So our r hat 3, 1 will be equal to the value of R3 minus R1 over the absolute value, okay? So R3 minus R1 all over R3 minus R1. So what is R3 minus R1 actually? That is our position vector from 3 to 1. So what is R3? R3 is 0.8. So 0.8i. Notice it is in the positive axis. So we are going positive. So 0.8i minus R1. What is R1? R1 is this, 0.6. 0.6. Okay? So that will be minus 0.6j. Minus 0.6j. Okay? All right? So then the magnitude of this will be equal to the square of this, the square root of the square of this, plus the square root of this square of this guy. So square of this guy will give us 0.64 plus 0.36. That is 0.164. That will be 1. So square root of 1 equals 1. Okay. So that is 1. So it means that the r hat 3, 1 will be equal to that. This the value of this vector, which is here, 0.81 minus 0.6j all over. It's just the same process as what we did initially. Over 1. Okay? So over 1 is over 1. Doesn't change. So this will be it here. Over 1 does not affect it. So we'll multiply this by our position vector, unit vector, which is now 0.81 minus 0.6j. Means I will be presenting our answer again in vectorial form. Then this guy squared. What is our absolute value here? 1, right? So 1 squared is 1. You see? Doesn't even affect it. So we'll have 9 times 4. That is 36. Or 24 times 9. Let's do 24 times 9. That becomes 216. So we have 216 times 10 raised to the power 9 minus 12. Then multiply by 0.8i plus, minus 0.6j. So from here, I'm going to have 0.3. This is 10 raised to the power minus 3. So that is going to be 1, 2, 3. 0.216. Does that make sense? Times this. Times this is in bracket. Minus 0.6j. By the time you use that to open the bracket, 0.216 times 0.8 is going to be 0.173 I minus 0.216 times 0.6 minus 0.129 or 13 J. 13J. So this is going to be our F. Force on 3 due to 1 will be this in Newton. Okay? So let's keep this somewhere. Let's keep it. Okay, let's keep it here and solve the second one here. I hope you have copied the questions. So now I want to find F32. So we want to find F3, 2. That becomes KQ3 Q2 over R3 minus R2, absolute value of that, R hat 3, 2. So our R hat 3, 2. Now there is something about, okay, we can apply it here. I'm going to show you something. Now our unit vector, R hat 3, 2 will be equal to, first we have to find this, right? Let's find this. That will be R3, the position vector R3 minus R2. R3 is 0.8. R3 is 0.8. So 0.8 minus 0.6. Okay. This is I, this is J. Okay. Then the absolute value of this will be equal to, this is the same thing. So that will be 1, 2, okay. Why is it the same? Okay, yeah. We are giving the same distance. Okay, we are giving the same distance. All right, let's keep going, So we now have our F3, 2 will now be equal to K, which is 9 times 10 to the power 9 times Q3, 4 times 10 to the power minus 6 times Q2, minus 0.6. So you see, I didn't even include the minus. All over our unit vector 1 times 0.81, our unit vector. Right? Our unit vector is going to be this guy over 1. Yes, this guy over 1. So it's going to be the same thing. Pretty much what we did here. Exactly. Yeah, what we did here. So which is still the same thing. I minus 0.6 J. Okay. So I think it's the same thing. This is 0.6. Okay, this is 6, sorry. This is 6. It's actually the same thing. 0.216 Yes. It's exactly the same thing. I think there's a mistake somewhere. So, because I did exactly the same. This is 6 microcoulomb, this is minus 6. Uh-huh. How did we get this? We said 0.81 minus 0. Okay. This is supposed to be positive, yes. All right, sorry. I I saw the mistake that I made here just now. And for what I solved, it was supposed to be, what I did in my book was to make, that was what I wanted to explain the other time. You know that I said that the position vector for 3, 1, for example, position vector R31, the position vector, the for force 3, the force on 3 due to 1, the position vector will be 1, comma 3, right? I mentioned this, okay? So if you want to solve for the magnitude of this, so that will be equal to R1 minus R, position vector R3. So what is R1? R1 is 0.6 in this direction. I think there is even a minus in the question. There's a minus in the question. So it will be minus 6 in this direction, right? Then in the upward direction, minus positive 8. So that will be minus, so in this direction, my 0. This j, 0.8j. So this is R13. But what we are looking for is actually R3, 1, right? So recall that the values, the magnitude of R31, position vector R31 and position vector R13 are actually the same, but so which means that they are commutative. They are actually non-commutative because the value, the sign changes. So R31 is actually negative R13, or R13 is negative R31. Does that make sense? R13, negative R31. So R13 here is going to be the R3, 1 will be equal to negative of this, negative minus 6i minus 8, 0.8j. So if that be the case, everything becomes positive. So here, we are supposed to be using positive. Does that make sense now? We are supposed to be using positive, positive. And you might be wondering where I brought this from. You remember that I said that the formula for F31, for what I said here, for F31 will be equal to KQ3Q1 over the position vector R13 dot the unit vector R31. I already mentioned this, right? So that's why I'm bringing this. Okay. So if you use this or use this, you get the same answer. That's my point. Whether you use negative, negative, or use positive, you get the same answer. So that was what I displaced here. So positive here. So it doesn't really change so much. So, but it will interfere with our answer here because it's not supposed to be exactly the same. That's what I was thinking. So here, positive. So here, positive, here, positive, here, positive. All right. It doesn't really affect much from what I'm saying though. Okay? Just the sign convention. Okay? And there was also something I misplaced here. I didn't put the sign here. I didn't put it. And I am supposed to actually put it in my working. Sign convention matters with vectors, please. Sign convention matters with vector. Because from what I solved, I saw that it would give me a negative answer to out here. Does that make sense? So you include the charge. Except if you are solving scalar. I'm used to solving scalar, that's why. If you are solving scalar, this sign does not matter. But if you are solving for vector, you have to put the sign. Okay, just as a way of so one of what we'll do is we're going to solve this like a scalar. Exactly. In fact, the question is never given with vector notations. So now to reaffirm what I was saying the other time, this f force on 3 due to 2 will be equal to kq3 q2 over position vector r2 comma 3 this way, okay, then dot r hat 3 comma 2, okay. So with that said, if you multiply this, you still get 0.216 into bracket. Is that incorrect? 40? Yes. Into bracket, all of this 0.8i minus 0.6j. Okay? Which is exactly what we had before. So, but negative this time, negative, please. Okay? Because of that negative there. So now I have negative, this will open the bracket and give us positive negative 0.173i plus minus times minus plus 0.13j, yes, or Newton, yes. So that's our, okay, then our final answer will now become F3 net will now be equal to F31, which is this 0.173i plus 0.13j plus F32, which is this. This is F3, 2, okay, which is negative 0.173i plus 0.13j Newton, okay. By the time you open the bracket, it becomes 0.173i plus 0.13j minus 0.173i plus 0.13j. Okay? Okay, yeah, so this takes care of this. Yes, 0. Then this plus this, 13 plus 13 is 26. So we have 0.26j, yes. So this will be the answer. So that will be, okay. You see, I have one more question. All right. I hope what I did is clear. Yeah, with vector, when you are solving vector, you have to be more careful. So, all right, so 4-point charges of this magnitude, that magnitude, that magnitude, Coulomb are placed respectively at corners A, B, C, D of 5 centimeters square. So if we have a 5 centimeters square, let's call this edge of this square. We say A, B, C, D. A, B, C, D. So this charge is placed here. This one, 10 raised by minus 7 coulombs. That one, minus 10, is placed at B, since it's respectively minus 10 raised by minus 7 coulomb. Minus 2 is placed at C, minus 2 times 10 raised by minus 7 coulomb. Positive 2 is placed as D, times 10 raised by minus 7. Everything is minus 7 coulomb. So they are placed respectively at the corners A, B, C, D, or 5 centimeters squared. So we have 5 centimeters squared. So everywhere here is 5 centimeters. So let's convert. That becomes 5 divided by 100, 0.05 meters. So here will be 0.05 meters. Find the magnitude of resultant force on the charge D. So let's find the magnitude of resultant force on this charge D. The magnitude of resultant force on charge D. Okay, so let's start with the force on charge D due to charge A or charge C. Let's go in alphabetical order. Due to charge A, that will become KQD QA over R squared. There's no need for position vector here, right? So we can just go on like this. So we have K, which is 9 times 10 to the power 9, multiplied by Q sub D, which will be 2 times 10 to the power minus 7 times QA times 10 to the power minus 7 all over R squared. The distance is 0.05 all squared. This becomes 9 times 2, 18 times 10 to the power 9 minus this, that's 14. So all over 5 squared is 25. 0.0 squared, that would be 0.00000. So that's times 10 to the power minus 4. So what we have is 18 divided by 20 times 10 to the power 9 minus 14 is minus 5. So minus 5 minus 4. I hope this is clear. Division is this minus, subtraction of power, then minus 4, minus 4. So 18 divided by 25, what does that give us? 0.72. 0.72 times this. So 0.72 times 10 to the power minus 5 plus 1 plus 4. That's minus 1. Okay? So our answer pretty much becomes 0.072. Okay, Newton. All right. So force on D due to A will be 0.072 Newton. Okay. Now let's solve for FDB. Force on D due to B. That also becomes QD QB over R squared. Okay? Now, K is equal to 9 times 10 to the 9th times Q sub D, 2 by 10 to the minus 7 times Q sub B, 10 raised to the power minus 7 all over R squared. R squared is 0. Now R is the distance between them, which is the separating distance. That's here. This is our R. So how do we find that? Let's quickly do a little bit of geometry here. We're looking for X. We already have this guy to 0.05, this guy 0.05, so that, no problem. There are actually chairs in this other assessment. So the hypotenuse will be equal to 0.05 all squared plus 0.05 all squared, and h will be equal to the square root of this. This squared is going to be 225 times 10 to the power minus 4 times 25 times 10 to the power minus 4. So 625 times 10 to the power minus 4 minus this, minus 8. So square root of this times 1 over 2. So we have square root of this is 25. This and this, we're looking for this. Okay. So 625 times 10 to the power minus 4. And this becomes h. That will be 0.00 0.05 and 0.05 plus, I'm sorry, this is supposed to be plus. So this becomes 25 plus 25, that's 50 times 10 raised to the power minus 8. So square root of this. So that becomes square root of 50 will be 25 times 2, which is 5 root 2. So 5 root 2 times 10 raised to the power. Now this will be 10 raised to the power 4. It's addition, not multiplication. So the square root of minus 4 will be 1 over 2. So 5 root 2 times 10 raised to the power minus 2. So that's our h value, the value of the hypotenuse. All right, so then, so it means that here we have 5 root 2 times 10 raised to the power minus 2, or 0.05 times root 2. So it's basically the same. Okay, so we've gotten our distance of separation. So that becomes 5 root 2 times 10 raised to the power minus 2 all squared. Okay, so what we'll have is this times this, 18 times the same thing, pretty much what we had on top. 18 times 10 raised to the power minus 5. So FDB will be equal to 18 times 10 raised to the power minus 5 all over R squared, this squared, 5 root 2 squared, 5 root 2, 5 root 2 all squared is equal to 50. Oh, yeah, 50 times this square, there is power 4, minus 4. Okay? So what we have will be FDB will be equal to 18 over 50 times 10 raised to the power minus 5 minus 4. The same thing we had here. So this becomes 18 divided by 50. That will just be half of this. 18 divided by 25, half of this. That will be 0.036. Let's confirm. Okay, yes, 0.36 times 10 raised to the power minus 1. Okay, then 0.036 Newton. Okay, so that's FDB, that's force on D due to B. Now what will now be FDC, force on D due to C. This will become force on D due to C will be equal to KQD QC over R squared. So 9 times 10 raised to the power 9 times QD, still 2 times 10 raised to the power minus 7 times QC. Okay, this one is now this 2 times 10 raised to the power minus. Look at the way I just eyeballed the minus now. R squared, the same 0.05 all squared. So we have this by this by this. That will be 36 times 10 raised to the power 9 minus 14 over 25 times 10 raised to the power minus 4. So we have 36 divided by 25. That will be 2 times of this. right? 2 times of this will be 1.4. Because if this times 2, right? Times 2. So that will be 1.44 times 10 raised to the power 9 minus this, minus 5 minus 4. Okay? So this becomes 1.44 times 10 raised to the power minus 1, which equals to 0.144 Newton. So this is FDC. Okay, so the last step, or the final step, the final step says that we should calculate the resultant force or at D. So F resultant will be equal to the sum, the vector sum of the forces on x-axis plus the vector sum of the forces on y-axis. So that will be the resultant force. Okay? So what are the forces on x-axis? The forces acting on x-axis, we have the FDC. FDA will be 0 because it's acting on y-axis. So FDC, which is 0.144 Newton plus, which one again is on x-axis? So this one, B, we are going to resolve it to both x and y-axis. So resolving to x-axis, the angle here, we will assume that it is on perfect 45 degrees. So that will be 45 granite here. So that becomes, we'll be closing it by resolving to x-axis. That becomes the FDB cos theta. So what is FDB? FDB, which is FDB 0.036 cos 45, then plus 0, which is FDA. Then summation of guys in y-axis will be equal to 0. On y-axis, FDA is exactly on y-axis. That will be 0.072 Newton plus 0. FDC is 0 because it's only on x-axis. Then FDA, will resolve it by opening the angle. That will be sine 0.3, FDB rather, FDB 0.36 sine 45. Sine 45 and cos 45 are the same, so that is 1 over root 2. That will be root 2 over 2. So F sub x will be equal to, let's just use my calculator for that. Fx will be equal to 0.036 times cos 45 is equal to then plus 0.144. F sub x gives us 0.169 plus 0.036 sine 45 plus 0.072. That gives us 0. This 0.144, that's FDC, okay. 0.097. So by the time we add that, this f sub y is equal to 0.097. Okay? So our f sub r will be equal to this 0.169 plus 0.9097. 0.169. This becomes 0.266 Newton. And that is the final answer. If you are told to find the angle between them, you take tan theta is equal to summation f sub x. This is summation f sub x, summation f sub y. That will be summation f sub y 0.097 over 0.169. Then you take the tan inverse and you get your answer. This will be it for this video. If you did watch the video to the end, provide the answer to the theta, to the angle between them in the comment section. God bless you and subscribe to the channel.